So, questions? Maybe I can, yes, okay. There is one question here.
Thank you very much. Patrice Mangin from Trois-Rivières University. Nicholas left me on my hunger. Like from starting 2009 in the demonstration, first bail 11 years. Now the boat sailing for a full year and more, which is the commercial plant. What's your timeline about? Because, you know, we have these innovations, which is marvelous. But if it takes 15 years to get to the product, the market is changing and the society is changing. So do you have an answer? All of you, by the way.
The whole process, as Nicholas said, and we have went over also yesterday, started somewhere 2008. So that's a long time to hear. But actually, in the beginning, there was, I would call it lag time, when we were trying to understand what we are actually doing. And it was only somewhere in 2017 when we actually found those solvents what are being applied now. And it's actually after that the development has been fairly fast. So in a way, it also tells a little bit on the time frame of research, because if you're doing research in the laboratory, you're normally working at maximum maybe a few grams. Then you start piloting it like Aalto did. They require something which is minimum of few kilograms, and there's upscaling to that, and then upscaling even to bigger scales. And every time you're actually facing new challenges. So it's when you're talking about the big process like this one, something which may be a side product or impurity at 1% scale in the laboratory, you won't even notice it. But actually, if you're talking about tens of tons of chemicals, 1% is actually pretty much. And especially in that scale, it also means that we have been actually developing several things, let's say parallel or in collaboration mode, both the scaling up of the solvents, because you can buy these actually from Sigma-Aldrich as research chemicals. But the price for those is far beyond what you could afford actually using in a real operational plant. So there has been development or upscaling of the chemistry, but there has been also upscaling of the technique how to actually make the fibers. And especially when we are talking about the upscaling of making the fibers, that has been really fast in my opinion. So please, Herbert, continue from this.
Yeah, very good question. Of course, process in general, I have to state, process-related innovation has a much longer time scale as anything else, like IT-related one. And I think to answer a little bit this question, I think it's good to look back. How was that in previous innovations, which finally ended up in commercialization, like the classical NMMO-based lyocell technology. And I mentioned the first patent was filed in 1939, and the first commercial plant came on stream in 1992. And you had 3-4 powerful companies in the back. That's not what we have at the moment. So we are an academic institution. And of course, we benefit from all the developments which were occurring at that time, because we also use this air gap spinning technology. But I would say this is the one thing. The other thing is, of course, also the background and the money you invest. Of course, when you invest more money, research money, but also other money, especially when you collaborate with big research institutions, especially from a company, then, of course, the development might go much faster, because the conventional operation of the processes are there established, while this is needed to be built up in an academic environment first, what also has been mentioned. So when my colleagues, especially in the academia, our president and our dean asks, what are the development phases? Yes, we start, and in 2 years we know everything what we should know within the pilot plant. In another 2 years we know everything from a demonstration plant, and in 5 years we have the first commercial plant. Bullshit. It's not going to happen. So unfortunately, and I think it's not really a secret, the first, let's say, money you earn from a lyocell plant was not before, let's say, mid of 2005, 2010. And it's very important also for you, Metze Fiber, you have a strong production of pulp and paper to finance your investment in innovation.
Very good. Niklas, if you can respond quickly.
Yeah. It's just unfortunately so that engineering and building a demo plant takes about 2 years. It could have been a bit shorter, but we came just into the pandemic when we were almost ready. But 2 years, then you need to reserve 2-3 years for the actual demonstration work. And then you start again, engineering and building, and the big plant is 3 years. So this is, you cannot really change this if you want to start a completely new production process.
Thank you. More questions, and I would like to ask to make the questions short and the answers also short so that we can cover as much ground as possible. There is a question there from one of the researchers participating in the poster sessions.
Yes, thank you. My name is Alexandra Kozłowska. I'm from Chalmers University of Technology. I have a question to Dirk, actually, from Euratex. I mean, it's so nice to see that you, of course, create in the European Union is working so hard on the creating new legalization. And of course, we are all aware of the drawback of the fast fashion. But what about the education of the society and customers? That's something also what Orlando highlighted at the end. I would like to know if the European Union has any plan to advertise what are the drawbacks and what is the advantages and how to change the thinking of the society.
In the textile strategy, the need to focus on the consumer is recognized. The Commission is proposing a campaign which we'll call Refashion EU, like #Refashion EU. We just announced that they will roll out the campaign. We don't know any details. So you can say at this stage, the Commission recognizes that we need to address the consumer. We as an industry insist on that. As I said before, we as an industry increasingly work with the brands to kind of join forces into educate is a strong word, but inform the consumer about environmental impact and etc. So I would say the good intentions are there, but there is work to be done in the years to come. So to make sure that it's not just good intentions, but that we actually roll out this campaign with resources, with transparency. I mean, we have too many labels. We have too many green labels. Every brand is using its own green cards, whatever it's. So we have things to do on our side in being more transparent, and then we need again joint forces between the authorities, the industry, and the brands. So let's hope it will. At least we will try to push to make sure that it actually happens. It's not just intentions.
Thank you, Dirk. Mm-hmm. I think we're all consumers. I'm a consumer, and I have a question, actually. So I tell my students my favorite suit and pants are the ones that I used in my PhD graduation in '98. And I still use those. I should have brought those today, because really I use them as an example. They are pretty much a lot of polyester. So my question to the speakers is how far are we from getting this long durability, in the polyester-like materials? And I mean, what is the development that we need to see in this direction?
Yeah, good question. So I tried to, in my talk, I tried to emphasize the criteria relevant to durability of textile fibers. So one is certainly the integrity of the fibers. That means also the intrinsic strength properties. So that's an issue, but not, of course, only under dry conditions, under wet conditions. That's very important. And I think H&M quoted that they refrain from using viscose fibers, probably because they have some, let's say, not very good properties under all circumstances. That's understood, of course. But I would say the new generation of lyocell type fibers, they are very cotton-like. So we have certain challenges. This is the so-called fibrillation. The fibrillation is a property which is more or less an intrinsic property because of the high orientation of the molecules. The lateral adhesion between the crystallites is weakened, which then facilitates the split off of surface fibrils on wet abrasion. That's a point. But there are ways to remove, to inhibit that, or to at least reduce this degree of fibrillation. I would say we are in a good way to be able to produce durable fibers. Of course, we are talking about cellulosic fibers or natural fibers. There are certain properties which cannot be attained using cellulose or natural fibers. Cellulose is a very hydrophilic polymer, as you know, and it's terribly difficult to render cellulose, let's say, a permanent hydrophobicity. That's the problem. So for outdoor applications, we have also with our students, we try a lot of options, but let's say, to combine both green chemistry methods, don't use any fluorhydrocarbons and silane-based compounds and so forth. And in addition, also to ensure biodegradability is very difficult. Yeah.
Thank you. Very quickly, Ilkka.
You were asking for short answers, but if the questions are like this, I mean, there are no short answers. The thing is that in every fiber or material made by man, like polyester, there are different qualities. Your suit is probably high quality because it's rather old already. On the other hand, it was actually pretty clear from what Herbert said today. It's the similar situation in man-made fibers. So there are applications where you don't need such a high quality, and then you can use different raw materials. And then on the other hand, you have the other end. So it also balancing, and there is actually a lot of more parameters behind this. So maybe that's...
Definitely. One question here, and if there are more questions, please raise your hand so we can locate you and have the microphone on time. So please, any other questions, raise your hand. Please.
Is there a difference between different wood fibers for textile?
Indeed, yes, there is. So we basically summarize this category of fibers in so-called either man-made cellulose fibers, that's one title. The other would be regenerated cellulose fibers. But that does not include, for example, cotton. So that's a natural fiber. And these regenerated cellulose fibers, the typical grades are depending on the processes you use. The viscose process, for example, is of course determining to some extent the resulting properties. Even though, and that's quite nice, we have an expert here on viscose sitting in the audience who could explain it much better. But the viscose, why is it still alive? Because it had the highest flexibility in tuning the properties compared to any other process. So it was already thought that it will die after Second World War. And then a person named Cox invented a modifier. Adding this modifier was capable of extending the state where you can stretch this solution so that the molecules align in parallel, which give high orientation, and that way then these so-called high wet modulus fibers, which are very, let's say, comparable to cotton fibers, modal fibers, for example. So, and then of course the other type is the lyocell type fibers, which use a direct solvent, using also a different type of spinning technique, which results, let's say, intrinsically to higher tenacities and higher properties, especially under wet conditions.
Ilkka, you want to complement the answer?
Yeah, I'll be very brief. We have to remember that there is actually, it was actually shown in the Herbert slides that there are other emerging technologies like the carbamate process, which is being scaled up with this Finnish company Infinity Fibers. There is mechanical treatments like what Spinova is doing. There's cold alkali or alkali, different types of solutions scaled up with other companies. And I don't think there is actually competition, because how I see it is that it's just a palette of opportunities. And of course, in the end of the day, we have to see the whole palette to make correct decisions. Is this process viable for the textile fibers, or maybe the other one is for non-wovens and the third one for something else?
Yeah. There is a question in the back.
Yes.
Gabriel? Yep.
Hi. Gabriel Bonville from the University of British Columbia. I have a broad question, so it's for the laureates and maybe also Mr. Eckenbach from H&M. So in the ion cell process, you chose to produce fibers in order to have a fabric as a final material, right? But in theory, you're not limited to producing fibers, and you could shape the cellulose solution into any shape, for example, film extrusion, right? And you could even change the surface to change the filling. So do you think your technology could change the way we produce clothing by directly processing it into the desired shape without having to use fibers as a transition material? Thank you.
Thank you for the question. Actually, it's even more than just putting it into different shapes. Yes, that should be possible. It's not yet there, but there is also another rather unique property of these solvents, because you can also use them for chemical modification. So it means that you can have different types of materials from cellulose. I mean, nowadays the other modified cellulose products is basically more or less like cellulose acetate. But here we can actually make a lot more chemistry. For example, there are already good examples of producing cationic cellulose, which is a water purification chemical. The beauty of that is that you apply it for precipitating the particles from wastewater. But after it has done the job, it actually decomposes back to cellulose, and that is biodegradable. So actually I see this, that you might have one line which is actually using the same dissolution technology used for making man-made fibers, but then you can have side pipes or so to produce other products. So it's not only that we are talking about textiles. Yes, there are other possibilities, definitely.
Martin, do you want to add anything?
Yeah, I can add, I mean, we're looking into several opportunities with cellulose as well. It's looking at sequence, for example. How do you create these small shimmering effects on party dresses or kids wear from cellulose? Or how do you create accessories from cellulose feedstock as well? So we're looking into all what you can do with cellulose-based feedstocks as well. I think to create something else than fabric, to create textiles, then you are quite limited to creating like panels for garments, and that's quite a small area. But for other applications, definitely.
Thank you. Maybe you could mention that. Other questions? I was noting that in the investments that I see startups, actually a lot of funding is coming to biology. And that was one of the H&M's ideas, to grow cotton in the lab. So do you see synthetic biology and biological methods to build molecules up as a possibility in this area? Given that what I see is a huge investment, actually the largest in startups are going to biology routes.
Yeah, very difficult question because I'm not a biologist, but I have a clear idea on that. This is also due to the age, advanced age. There was a professor called Professor Brown, and he wanted to raise algae in the Bay of, Florida, to produce algae, but of course never worked out. And also to use carbon as a source for fermenting new biopolymers is not a good solution. We have the best biopolymer with the cellulose and other biopolymers. So I'm not at all convinced. I know even big companies like DuPont try to use, let's say, biochemically produced biopolymers like Kurtlan or 1,3-D-glucan and make very bad fibers out of it.
Okay, different opinion, Ilkka?
Not a different opinion, but actually, if you are using fermentation, like we are producing beer, I mean, then we have the yeast, which is basically also containing proteins. And actually, these particular solvents, what they are talking about, they are pretty good solvents for proteins. So, yes and no. So maybe not for the cellulose, but actually there might be possibilities in the side streams, which is not at all looked at least to my knowledge.
Yeah, good point. More questions? There is one there.
Yeah, thank you, Maija Tenkanen from University of Helsinki. Actually, following up this question, a little bit like intriguing thing is that do we need trees? Can we have it as a cell culture? It was discussed about cotton, but what about, I mean, if cellulose is so great, so do we need to have the forest for that? Or can we make it more? I know that you are not an expert on that, but kind of a Orlando's question like activated me to ask this.
Yes, we do. The thing is that yes, there are possibilities in making these kind of things, but actually, if you use actually cells to produce something, for example, thinking about Finland, I mean, we have a winter, so it doesn't. It's not. I would claim that it's not yet there. We have much better biochemists and biologists here in the audience. I'm sure Kalle Kahnberg could, for example, answer that question much more detailed than I am capable.
Yeah. I didn't want to distract from ion cell to biology, but I think it's a relevant question to ask. So very good point. But maybe Johanna.
Yeah, just to comment, so that when we are utilizing microbes to produce something, we need carbon and nitrogen. And where does the carbon come from? Do we first grow the tree or the plant, then we degrade it to monomers, then it contains inhibitors, which are attacking the microbe, they are not letting it to work as it should. And then we are doing very tedious downstream processing on the liquor. I have been working with this fermentation of biomass hydrolysate, so I know it's not that easy. So maybe we could utilize the wood or the plant.
Herbert.
I fully agree to that. But there is another point I would consider. We have Mother Nature makes so excellent biopolymers. And of course, we talked about wood now, but we have also annual plants, we have agricultural waste, and I think that is certainly the second most important source for the future. There is one, looking to H&M, there is one intrinsic disadvantage, or actually more intrinsic disadvantage of cellulose. It does not melt, so we have to basically make a sidestep to produce a kind of spinning solution by selecting a good cellulose solvent to eventually increase the cellulose concentration. So there is already a progress. When we look at viscose, we have, let's say, in the best case, 9% cellulose in the solution. Now we talk about 13 to 17%, but it's actually not very good. So we need to go to 40, 50%. Yeah? And the other thing is, you were talking about we urgently need something which replaces elastane. I fully agree. But what is it? So elastane is such a terrific polymer which, to my knowledge, has not ever been, let's say, challenged by other biopolymers. Yeah, not at all. So this is something what we are really working on also. And of course the other and the last thing is tuning hydrophobicity, hydrophilicity, as I mentioned already, while maintaining the whole material environmentally friendly.
Ilkka.
Not directly related to cellulose, but as a continuation what Johanna said is that actually when we go to a shop now, we can buy a milk can where there's clearly a plastic screw cap, and what they state in this cartilage is that it's 100% bio-based. Yes, it is, but it is polyethylene. So what is being done is that they actually ferment first the sugars to ethanol, then they produce ethene, and then they polymerize it. But it's still the same polyethylene. I mean, this is greenwashing, in my opinion. And in the old days, people were actually using the wastewaters of sulfite paper pulping to make ethanol for other purposes, not to make ethane. And actually ethane was used to produce ethanol for the same reasons. So, I mean, it's not only that we are talking about this utilization of cellulose or making cellulosic products. This is all over. I mean, in all materials, and especially difficult materials are when these components, like synthetic polymers, are mixed with natural fibers, like the coating of the milk can or something like that. There you have a problem with polyethylene, and I think that's much more severe than we guessed it is.
Major problem. We're a little bit over time. Maybe we can entertain a couple of more questions. Please, Alexandra.
Yes, I have another one actually.
Just the microphone, just a second.
Thank you. It's a little bit more technical from your presentation. I'm quite interested. Why did you see the upscaling of the strength in the cotton post waste? You know, those green and yellow slides you showed. So you said that the strength of the material increased. Is it due to the application of different solution, or is it because of the spinning process? Do you know what?
The answer was given by Frank Meister. The cotton has a very uniform molar mass distribution, and that's essential because when you have a certain share of short chains, as you typically have from wood pulp, this weakens, of course, the fiber. So there is a clear, almost straight line correlation between a certain fraction of short chain and the final tenacity. So we like cotton waste.
Yeah. One more question. Okay, maybe we can close with a question I wanted to ask Herbert again. And this idea of transition between university and industry is a quite important one. And pretty much oftentimes we scientists don't look into what is the need in industry, in society, and there is a disconnect. So how do you see the work?
And vice versa.
And vice versa. So what is the way to bridge that dilemma?
Yeah, I think this is an excellent question. And I like to interact with all the parties, even with institutions like EU. It's important to understand what is going on. And my special concern is, because I see it, young researchers very hungry for research and have their, of course, their focus typically continuing their PhD work. But this would be the moment where they go out and have a sabbatical in industry and learn the real requirements, what Niklas also mentioned. So this is totally different when you do something in the laboratory and then you want to gradually do it in commercial scale. Yeah. And the same also applies to R&D people from companies or even production people to spend a certain time in academia and to more or less mutually influence each other.
Very important. Okay, I think This is all for today. It was really a big pleasure to host this event. I would like to acknowledge the participation of our steering group, the selection committee, who has driven the process, have made the selection of the speakers, and of course also the laureates. We're very proud of you, your work, and congratulations on our behalf, and congratulations all of you for staying today, asking good questions, and thinking all together about the future of textiles wearing wood. Thank you.